This video is for Lesson 2-2, Deductive Reasoning. The learning goals are to use deductive reasoning to prove that a conjecture is true, and to develop geometric or algebraic arguments based on deductive reasoning. In math, there are certain methods and rules of argument that mathematicians use to convince someone that a conjecture is true, even for cases that extend beyond the observed data set. Remember, in the previous lesson, we discussed inductive reasoning using observations to make conjectures. We don't know from inductive reasoning if our conjectures will be true for all examples. We only know that they work for our observed data set. So there's another form of reasoning that creates some more solid proof. This is called deductive reasoning. Deductive reasoning are when you use rules of logical reasoning to create an argument. The argument that follows from using those rules is called a proof. A statement or conjecture that has been proven is called a theorem. And a proof transforms a conjecture into a theorem. In geometry class this year, a lot of our theorems will be about shapes. But to start off, let's discuss some theorems about numbers. So below are some definitions from arithmetic. An even integer. An integer that has a remainder of 0 when it is divided by 2. The definition of an odd integer is an integer that has a remainder of 1 when it's divided by 2. In the following items, you will make some conjectures about the sums of even and odd integers. Question 1. Calculate the sum of some pairs of even integers. Show some examples and make a conjecture about the sum of even integers. So here in purple are some examples. I added even numbers and got answers, and I observed that every time I did that, my answers are even numbers. So my conjecture is that the sum of two even integers is an even integer. This process that I'm using here is inductive reasoning, using some examples to form a conjecture. Number 2, calculate the sum of some pairs of odd integers. Show examples and make a conjecture about the sum of odd integers. So here I've selected some odd numbers, added them together, and looked at the answers. 2, 4, 8, 18, 60. I observed that my answers are always even numbers. And so here's my conjecture. The sum of two odd integers is an even integer. Again, that's inductive reasoning. I know that that's true for some examples. I don't know for sure that that's true for all possible examples. Number 3, calculate the sum of pairs of integers consisting of one even integer and one odd integer. So here I've thought of some examples, an even plus an odd, an even plus an odd, an even plus an odd, and looked at my answers. They appear to always be odd numbers, and I've written that out here as a conjecture. So how do we know whether those conjectures are true for all possible numbers, not just the ones that we used as examples? Let's do some work with this. The following items will help you make a convincing argument, called a proof, that supports each of the conjectures we made in items 1 through 3. Number 4, figures A, B, C, and D are puzzle pieces. Each figure represents an integer determined by counting the square pieces in the figure. Use these figures to answer the questions. So this puzzle piece is representing the even number 10 because there are 10 squares. This is the even number 6. This here is the number 11. And this one here is the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus the odd man out. That's the number 13. Question A, which of the figures can be used to model an even integer? That would be figure A and figure B. Question B, which of the figures can be used to model an odd integer? That's C and D. So question C, compare and contrast these models. Well, what I notice about A and B is that they can be divided by 2 with no remainder. They are these rectangle shapes at the top of the video. If I divide them by 2, just split right down the middle and create 2 groups, there is no remainder. I notice these are rectangles. C and D will have remainder 1 when divided by 2. And I notice that they are not rectangles. Now number 5, which pairs of puzzle pieces can fit together to form rectangles, make sketches? Well, if we take A plus B, this is shown here in this drawing, that creates a rectangle. If we take C plus D, those two odd ones, and fit them together, that creates a rectangle. Number 6, explain how the figures, when used as puzzle pieces, can be used to show that each of the conjectures in items 1 through 3 is true. Our first conjecture was an even number plus an even number always makes an even number. And our puzzle pieces help because A plus B made a rectangle. Again, A was an even number, B was showing an even number, fit them together, and that created a rectangle, which is an even number. Our second conjecture was an odd plus an odd is equal to an even. And that's shown with the C plus D fits together to make a rectangle. The third conjecture, an even number plus an odd number, is always equal to an odd number. If we took A plus C, A plus D, B plus C, or B plus D, and fit those together, they would always make a shape that had that extra square on it. Again, here are the figures. So as an example, if we were to take figure A, the rectangle, tack figure C onto the end of it, it's always going to have that extra odd piece. It's going to be an odd number. So in items 5 and 6, we proved our conjectures geometrically. We used shapes to prove it. In items 7 through 9, let's prove our same conjectures using algebra. The algebraic definition of an even integer is right here. An integer is even if and only if it can be written in the form 2 times p, where p is some integer. What we're saying is if p is any integer, then if you times it by 2, that's going to create an even number. We don't have to use the letter p when we write an algebraic model for even numbers. We can use any variable we want, like m or n or whatever. So number 7, use the expressions 2p and 2m, where p and m are integers, to confirm the conjecture that the sum of two even integers is an even integer. So let's take our first expression, 2p, and add the other one, 2m. Again, we're working with the sum, right? So here in algebra symbols, we're showing a sum of two even numbers. This number is an even number, and this one's an even number. Let's factor out the common factor of 2, sort of like using the distributive property in reverse, and we can write it as 2 times p plus m. But this structure that we create is that same structure up here in the definition of even numbers, that 2 times some integer is going to be an even number. So that shows algebraically that adding these together creates something that is also an even number. The algebraic definition of an odd number is right here. An integer is odd if and only if it can be written in the form 2t plus 1, where t is some integer. Again, it doesn't matter what variable you're using. Number 8, use expressions for odd integers to confirm our conjecture that the sum of two odd integers is an even. So here is an odd integer, 2t plus 1. Let's add another odd integer, 2n plus 1. Kind of grouping them a little tighter together creates this format. And again, there's a common factor of 2 that can be factored out of the following 3 terms. This structure fits our definition of even numbers, where we have 2 times any integer. If you add up an integer plus 1, you're guaranteed to get an integer. So this is 2 times some integer here, and that is the form of an even number. Now question 9, use expressions for even and odd integers to confirm our conjecture the sum of an even and an odd makes an odd. So here is some even integer. let's add some odd integer. Group them a little tighter together, and then for the first two terms, factor out that common factor of 2. That creates this result. M plus n is some integer number. And so this has the form of an odd number. In items 5 and 6, we developed a geometric puzzle piece argument to confirm our conjectures. And in items 7 through 9, we used an algebraic argument. Even though one method is considered geometric and the other is algebraic, they're often seen as the same argument. Number 10, explain the link between the methods. Well, here in green is one way to answer this. Defining an even integer as 2p is equivalent to using a rectangle that has 2 rows and p columns, or a 2 by p rectangle. And defining an odd integer as 2p plus 1 is equivalent to using a rectangle with 2 rows and p columns, but with an extra square on the end of it. Number 11, state the 3 theorems that we've proved about the sums of even and odd integers. And so here they are. They are those 3 conjectures we have made earlier that we used deductive reasoning to prove. So we went beyond what inductive reasoning was capable of, looking at a few examples. We've actually used both a geometric proof and an algebraic proof to show that these theorems are true. Here are some check your understanding questions. I'll pause the video. So in this lesson, we worked on these 2 learning goals. Use deductive reasoning to prove a conjecture is true. Our deductive reasoning was in 2 forms. We did a geometric argument using shapes, and we also did an algebraic argument using mathematical expressions and variables. That was that second goal.